Kenya iko sawa.
Ni Gen Z.
Hawa Gen Z walitusaidia pia.
They are being silenced by this politician. That's the problem.
No, but they have votes.
Using elimination method.
Yeah, but they are a big. It's a very big voting bloc now, the Gen Z. So eventually they will have to talk to them.
Yeah. That's why we want to show these people, prove these people come 2027.
Yeah.
That's the only thing we can do now.
The other option is you can also leave the country. You might get
you can also leave the country. Exactly.
There are a lot of, with the right organization, like for teachers, I think if you organize yourself well, there are a lot of opportunities for teachers outside Kenya.
Exactly. Even the UK. About the one for the UK.
Yeah. You just need to maybe put together your plans for 1 year or so to figure out what they need and work on that. Within 1 or 2 years,
exactly.
You can get a good one there.
Yeah.
Now, I think we want to start from this chapter 13.
Yes.
Characters. Ama mmeshasoma, najua huwa nauliza naweza kuwa nataka kufunza na mmesoma. Then I can relax if you have read. Now, there is this definition, the trace of a matrix, which is just a sum of the elements along the leading diagonal for a square matrix. I think that one is from the linear algebra side. Then some properties about the trace. The trace of A plus B is the same as the sum of individual traces, and the trace of AB is the same as the trace of BA. So the order in which you multiply does not affect the trace. And then the trace of this T inverse AT is the same as the trace of A. So for these ones, I will not go through the proofs, but carry these properties with you. We will need them as we go along. So this, what is here is just a proof for those theorems. So I will skip that. So the other definition we have is the main topic of the class, these characters of a module. So if you have a CG module, again, pay attention. The field is the complex numbers. So if you have a CG module, then this function that picks an element of G and sends it to the trace of this matrix is called the character of V. So that's the character of a CG module. Now, again, using the property that we saw earlier, the character does not depend on the CG module. I mean, the best choice of basis, you can work with any basis that you wish. It is independent of the choice of basis. Any basis that you pick will give you the same character. So it's invariant with respect to the basis, doesn't change. So that's an advantage. You can use any basis, the character won't change. This follows from, if you try to get the trace of this matrix on this side, it will be the trace of, remember the trace of this is the same as the trace of the matrix in between. This is based on the property that we just seen a few minutes before. This can be, it's the same as the trace of GB. So regardless of whether you pick B prime or B, as your basis, the trace will not change. So we can also define the character of our representation in the same way, but now we use the module we work with now is this CG module, CN. That's how you define the trace of a character. Remember, this is just a matrix. The row is a representation, so it will send G to a matrix. Let's call a matrix A. So if you want to get the character of a representation, then you will use to just be the trace of this matrix A, which is the image of G under row. So now we can say X is a character of G if it is a character of some CG module. That is one. Then we can also say X is irreducible if it's a character of an irreducible. It's actually chi. I keep calling it X. This symbol is chi, the Greek letter chi. This chi is an irreducible character. Again, if it's just if the CG module itself is irreducible, and of course, otherwise it's called reducible. So those are just mostly definitions. I don't think there's anything special there. So this is the one chapter where, in fact, he uses this ordinary notation for functions instead of this one. For the character, for some reason, he uses this ordinary notation. So this one says if any two CG modules that are isomorphic, they have the same character. And if any two elements in a group are conjugate, then the value of the character at those elements is equal. And this doesn't matter which character you pick, as long as two elements are conjugate, they have the same. The value of the character at those points is the same. So there is a theorem we learned earlier. Let's try to check this case where for the isomorphic CG modules. So if you have two isomorphic CG modules, then from a previous theorem, it's further back. There are two bases that give us this relationship, such that, and since the character does not depend on the basis, then if you get the trace, it doesn't matter which basis you pick. Since the trace, these two matrices are equal, so they will have the same trace. That's what follows. So this follows from this theorem 7.7, which guarantees that we can find these two bases, B1 and B2, satisfying this equation. And if these are equal, they have the same trace. And also, since the character is independent of the basis, then we are guaranteed that this is true. Doesn't matter which basis. So again, for conjugate elements, if X and Y are conjugate, then it means you can find some element G such that X is equal to G inverse YG. Now, if B is a basis of V, then we have the following. This X is just an element of a group. So this matrix that is with respect to this basis B is the same as the matrix for this element. And we saw earlier that this can be written as a product of these three matrices. And therefore the trace, because eventually here you're looking for the trace of this matrix. And based on this relationship, it will be equal to the trace of this middle matrix as well. We're using the facts that the trace of a matrix A is the same as the trace of this matrix T inverse AT for some invertible matrix T. So conjugate elements have the same character, or rather this function is constant over conjugacy classes. So the number of distinct values that it takes will probably be account of the not necessarily account, because that it may not be one-to-one function. So let's leave that first. The follows are examples, just getting elements, their images under the representation, and computing the trace. So that's what happens here. So for instance, for this example, one is set to this matrix, the trace is 2. So the character of the character at this point 1 is 2. The character at A is 0, and so on. A squared, you just add the difference. So there are 3 distinct values. There's 2, there is -2, and all the rest are 0. I think for this group P8, I think these 2 A and A cubed are in the same conjugacy class. Is that correct? I think all these are in the same conjugacy class. I think B A squared and A cubed B, if I remember correctly, or maybe not. You'll have to check anyway. But you can see the elements that are in the conjugacy classes have the same character. This one, of course, does not have any other element. A squared is the conjugacy class of A squared is just A squared itself. The same with 1, because you can see this value appears only once. So it means there's no other element that in that conjugacy class. If there was, this -2 would appear again. This one again is identity. It's the only element in its conjugacy class, so this value appears only once. Doesn't appear anywhere else. So for values that appear once, that clearly tells you that the conjugacy classes have only one element. So the next one is the same thing, but it's working with S3. So I think it's done for some elements of S3. Keep getting the sum of the diagonal elements, like that. So for S3, I think these 2 are in the same conjugacy class. So they have the same character. These 2, 3, and I think these are the reflections. The reflections are all in the same conjugacy class also. They have the same character. And then the identity. So there are those three conjugacy classes. So I think if you go back to chapter 9, this is an abelian group, C3. So it has these three irreducible characters. Yeah, so this basically is because this is an abelian group. You can go back and check in chapter 9 what it says about the abelian groups and the different representations. I think we had 3 distinct representations or something. I can't remember. I think that was it. So each of them will give you a different character. So this one is another example you can look at. It's now this one deals with D6, or D6 is the same as S3. It's not the same for other values of n. So for instance, S4 is not the same as, they're not equal. If you work with D8, it's not the same. And after 3, they're not equal, but for D6 and S3, they're the same. So now we look for another, we discuss another definition. It says if chi is the character of a CG module, then the dimension of V is called the degree of the character. So just the dimension, the degree of a character. This simply talks about dimensions, so I will skip the examples. So the next thing talks about the values of a character. If you have a character of a CG module, or any element G in the group of order M, then the following 4 statements will be true. The character at the identity will just be equal to the dimension of V. The character at G is the sum of the M roots of unity. M because our element G is of order M. And the character at G inverse is the same as the character of G. And the character of G is a real number if G is conjugate to G prime, G inverse. So if G is conjugate to its inverse, then the character of G cannot be a complex number. So let's go through them one by one. The first one says at 1, the character is just the dimension of V. So if you apply the character at the identity, you end up with the identity matrix. And the sum of the elements across the diagonal in the identity matrix will just be n, which is the dimension of V. Now, by proposition 9.11, because we're working with a CG module, this is possible. It's possible to get a matrix that is diagonal like this, where each W is each of these W's is an nth root of unity. This follows from chapter 9. You'd have to go back there to get the details. So the trace will just be the sum of its nth roots of unity. And that's what the second, it says the character is a sum of nth roots of unity. We don't know which ones they will be, but they will just know that there must be nth roots of unity. So the other, since here we take advantage of this structure, getting the inverse of this matrix is easy. So the matrix for G inverse will just be where what is on the diagonals are the reciprocals of what is on the diagonals for this matrix determined by G. Right? So then
Excuse me, Dr. Katende.
Yes.
Janet is requesting to be let in.
Okay. So to get a character, you simply need to add up all these things. So now the beauty about the roots of unity, the inverse of the roots of unity is simply there. It's the same as the complex conjugate of the value. So the W inverse is just the same as its complex. As long as W is a nth root of unity, W inverse is just its complex conjugate. Right? So if you can replace all these by their complex conjugates, so the character of G inverse is just the sum of the complex conjugates of the m's roots of unities that appear on the diagonal. But these quantities, if remember for complex numbers, if you add up this, suppose let's work with only 2 for simplicity, it's the same as the complex conjugate of the sum itself. So this is true for complex numbers. Right? So it's the same thing we're using here. So this sum of all these complex numbers is the same as the complex conjugate of the sum. But what is under this complex conjugate now is the character of G. This term under the bar is the character of G. So we end up with this. Now that means the character of G inverse will be equal to the complex conjugate. So where are we? It's here. It's a complex conjugate of the character of G. That's what we have proved. Now, if G is conjugate to G inverse, then they're in the same conjugacy class, and therefore will have the same character. But now we from the previous statement, we know that this statement is true, right? But now they have the same character, right? These two, so they don't have the same. They have the same character because they are in the same conjugacy class. But then that implies that this value is equal to its complex conjugate. And if any complex number is equal to its complex conjugate, if Z is equal to its complex conjugate, then that means this can only be true if Z is if it's a real number. So if G is conjugate to its inverse, that is, if they're in the same conjugacy class, then the character of G must be a real number. It can't be a complex number. So there's a special case, a little more you can say when you consider the special case where the element G under consideration as order 2. So with this special case, we can state the following, that if Chi is a character of G and G is an element of order 2, then the character of G is congruent to the character of 1, or the character at 1 modulo 2. So I think the important part is this order 2. It's an element of order 2. So we shall be working with the square root of unity. All these are supposed to be square roots of unity. Now, square roots of unity have only 2 options, either 1 or -1. There's no other square root of unity. So this will be a mix of 1s and -1s. So that's the first bit. Now, in total, the sum of the number of 1s and the number of -1s will total n. So we can assume that R of these roots are +1 and the remaining S are -1. So if you add up the elements, all the R1s, you get R, and add up all the S -1s, you get -S. So that will give you the sum of the diagonal elements of your matrix. So the character of G will just be R minus S, which you can. But we also know that the character of 1 is equal to N, or the sum of the elements in the leading diagonal for the identity matrix, which is, in other words, R plus S, because R is just a number of 1s and S is a number of -1s, but in total they should be equal to N. So, of course, the character now will be an integer. That is now one observation. And then this R minus S, we can rewrite it as R plus S minus 2S. But then that means it means R plus, the difference between this number, R minus S, and R plus S is divisible by 2. And therefore, these two numbers, R minus S and R plus S, are congruent modulo 2. Because the difference is divisible by 2. So we have confirmed that if G is an element of order 2, then its character will be congruent to the character at 1 modulo 2. So here I keep saying its character. There's no character of an element. I'm abusing the language a bit. It's supposed to be the character, the value of the character at G. So then we have the next theorem, which says if we have a representation of G, Chi is a character of the representation, then it says the absolute value, this is the magnitude of the complex number. This absolute value of the magnitude of the complex number will be equal to character of 1 implies that this matrix is a multiple of the identity matrix. And the other statement is that the kernel of the representation will be all elements in G whose and the value of the character of those value of the character of those elements will be equal to the value of the character at 1. So this is just the kernel of the representation. So this proof is, we can look at the first one. It says that this magnitude is equal to the character at 1 if and only if the value of the representation at G is a multiple of the identity matrix. So let G be an element from the group of order M. Now, if for some reason rho of G is equal to lambda IN, where lambda is a complex number, of course, then lambda must be an mth root of unity, because it means this matrix will just be a matrix full of lambdas all the way down and zeros off. So remember, these are supposed to be mth roots of unity. So the character of G will just be equal to the sum of all these values, which is n lambda, because there are n of them. If you add them up, you get n lambda. So the magnitude of G, if the magnitude of this now, if we have the following, I of G is equal to n lambda. So the magnitude of chi G will simply be the same as the magnitude of n lambda. But now this is the same as n times the magnitude of lambda. But what is the magnitude of lambda? Lambda is a square root of unity, an mth root of unity. So its magnitude is 1, right? So it's equal to n, but we already know that n is the same as the character at the identity element 1. So the converse will assume that this statement is true, and if it is true, it should show that this matrix that represents where is this statement? The theorem. Then this matrix should be an identity matrix. So again, with this assumption that the magnitude of this complex number, the character at G, if it's equal to the character at 1, we can use this fact that such a matrix exists, where each element in the leading diagonal is an mth root of unity. And the character at G will just be the sum of these mth roots of unity. And we made the assumption that this is equal to 1. So the character should be equal to 1. Now we're going to use some property of complex numbers, where it says if you have, we can start with 2. The magnitude of the sum of these two complex numbers will be less than or equal to magnitude of the individual So when you're adding complex numbers, it's usually like adding vectors, and each complex numbers can be represented as a vector. It's a coordinate it's a coordinate in R2, right? So you can think of it as a vector. So if you add the magnitudes of each vector individually, that is what you're doing on this side. You'll keep adding these magnitudes, right? These are the ones you're adding all the way. So, but if you add them, if you add up the complex numbers first, the final complex number will be the result. This is a complex number that you end up to be represented by this vector, if you are thinking of it in terms of vectors, right? So that's the complex number that you end up with. So this straight line the length of that would be the magnitude of this sum. But now this sum cannot be bigger than adding up these small distances. So that's what this does. So and the only time this will be equal is if the arguments of f are all of the same ones are all equal. So if the arguments are equal, it means they are pointing in the same direction. So that means when you add them, they will be added in a straight line. If the arguments are equal, it means arguments is the angle. Remember, you can present a complex number as r cos theta plus I sin theta. So if this angle is the same for all of them, it means they're pointing in the same direction. So if you add them, they will just be adding, you'll be adding them along the same line, one after the other. So they will be equal this distance, and the other distance of adding them individually will just be the same. That's the only time they will be equal. But we have this property of these complex numbers that each of them is of magnitude 1. And that forces all the in this matrix, it forces all these to be equal to 1, right? So what we are looking at is this: we have these complex numbers. So if you add them first, you'll get another complex number, but the magnitude will definitely be smaller than if you added each individual magnitude. So the last one is Wn. So we also know that each of these has magnitude 1. So it should be 1 plus all the way plus 1, which is equal to n. So, and what appears on this side now will be forced to be equal to n. It means the only time equality will happen is if these are equal. Is if all these numbers are equal, and we have, from the argument, we have seen that they must be equal, right? And therefore, if they're equal, it means they're the same number all through, and therefore you can write them as a multiple of the identity matrix as desired. So I will leave part 2 as an exercise for you. Part 2 of the proof. You can prove that. It's already done for you anyway, so you just need to read it. If you have questions, as usual, you can ask. So if K is a character of G, we can define the kernel of X of the character. I keep calling it X as all those elements that have the value of a character is equal to the value of a character at 1. So this is defined as the kernel of the character. The examples are just applying the definition. So I will skip the example to just simply apply the so this we have a new definition here where we say that the bar of the character chi, the bar of chi, is simply defined as its value is obtained as simply the bar of the value of chi at G. It's just a definition. So if you have chi of G, it's simple. I'm not writing anything new here. It's just the same as. So we're dividing this new function, which simply gets a complex conjugate of the old function, like that. So the claim is that this function will also be a character of G. And if this character is irreducible, then this character will also be irreducible. I think the proof is straightforward. I will skip it. I'm also interested in the regular character, but it's good for you to read and look at the examples. I think the rest I will leave as a reading exercise. It's a small part to read. I'll leave it to you to read. I have some urgent work to do today. So I think we have only one topic remaining. This is the last topic we will do. If you wish to read beyond that, that would be great. It's good for you. Just to obtain knowledge, but for purposes of examination, that we will stop at 14. And there are 2 chapters, 10 and 11, which I asked you to read. For those ones, if I'm to give anything, it will be on a takeaway card. But the rest will be examinable. So this is the last one which I'll do. 14. I think we can do this next week. So this is our next card, chapter 14. So there's a lot of reference to chapter, some ideas from chapter 9. So for this chapter 13 to make complete sense, you have to understand chapter 9 very well. So those 2 go together. If for this to make sense, if anything is not making sense here, you need to go back and read chapter 9 very carefully. Then everything will fall in place. So I'll stop there. If whatever we have done is not making sense, the parts I've asked you to read, if they don't make sense, you are free to ask in the next class then.